to mol-to-mol conversions. So the coefficients in a chemical equation are exact numbers because they represent the number of atoms involved in the reaction. Atoms are indivisible in chemical reactions, at least, so the coefficients are counting numbers, which are exact. That is, there is no uncertainty in our coefficients. For example, in the combustion of hydrogen, we have 2H2 plus O2 yields 2H2O. And that means that if we use 2 molecules of hydrogen, then exactly 1 molecule of oxygen will be used up, and exactly 2 molecules of water will form. We don't have 2 molecules of hydrogen using up 1.10 molecules of oxygen and producing 1.99 molecules of water. We have to get discrete numbers, so it has to be either 1 molecule of oxygen, or 2 molecules of oxygen, or 3 molecules of oxygen, and so on. And likewise for our products. We have to have discrete numbers of reactant molecules and product molecules involved in the chemical reaction. And this means that we can write equalities from balanced chemical equations. So 2 molecules of hydrogen used up equals 1 molecule of oxygen used up. Or 2 molecules of hydrogen used up equals 2 molecules of water formed. Or 1 molecule of oxygen used up equals 2 molecules of water formed. And we can then use these equalities to make conversions to use in conversion factors. So 2 molecules of hydrogen used up was equal to 1 molecule of oxygen used up, and so we can write our conversion factor either this way, or we can invert it and get this one, and likewise for our other 2 equalities as well. Note that the units in the above equalities on the previous slide and conversion factors are molecules, not moles. Now, because the numbers involved are ratios, we can then multiply the coefficients by some number, any number we pick, and the ratios will remain the same. Now note that we have to multiply all of our coefficients by that same number, otherwise we will change the ratio. Now this means that we can multiply by Avogadro's number, and the ratios won't change. So we can say 1.2044 times 10 to the 24 molecules of hydrogen used up equals 6.022 times 10 to the 23 molecules of oxygen used up. And note that this is a 2-to-1 ratio of molecules of hydrogen to molecules of oxygen. And then 1.2044 times 10 to the 24 molecules of hydrogen used up equals 1.2044 times 10 to the 24 molecules of water formed. And 6.022 times 10 to the 23 molecules of oxygen used up equals 1.2044 times 10 to the 24 molecules of water formed. But we can also convert these large numbers, which are fairly difficult to use, into moles. And we could say 2 moles of hydrogen used up equals 1 mole of oxygen used up, and 2 moles of hydrogen used up equals 2 moles of water formed, and 1 mole of oxygen used up equals 2 moles of water formed. And note that these ratios now of mole-to-mole ratios are the same as the molecule-to-molecule ratios that we had earlier. And thus, we can write our conversion factors in units of molecules or in units of moles. But be careful to use consistent units. That is, if you use moles in the numerator, you must use moles in the denominator. You can't use molecules. If you use molecules in the numerator, you must use molecules in the denominator. You can't mix them and say that 1 mole of hydrogen reacts with 1 molecule of oxygen. You can't do that. And this now brings us to the mol-to-mol bridge prompt. So in reaction calculations, after listing the wanted and data, if the wanted substance is not the given substance, then balance the equation using whole number coefficients, and then bridge by writing the bridge conversion. So X number of moles of your wanted substance equals Y number of moles of your given substance. And you should actually write in a number here for X, write in a number there for Y, and write in, instead of writing out wanted substance, you should write in whatever that wanted substance is, the chemical formula for that substance, and likewise for the given substance. And then you can use your bridge conversion that you've written here to solve. So let's look at an example. How many moles of ammonia, NH3, are needed to form 9.0 moles of water? So here we have a balanced chemical equation. If it wasn't balanced, you should be able to go through and balance it. So if I just told you that you reacted ammonia with oxygen to give NO and water, you should be able to fill in these coefficients here on each of our reactants and products. So let's write the wanted and data. The wanted is the number of moles of ammonia, and what we're given is 9.0 moles of water are formed. So the given substance is water, but the wanted substance is ammonia, NH3, and so we're going to need our bridge conversion. So we have our wanted here. We want to know how many moles of ammonia are going to be needed. We've got our data, our given of 9.0 moles of water formed, and now we have from our chemical reaction, from our chemical equation, we have 4 moles of ammonia are equal to 6 moles of water. And now we can go ahead and solve. So we take our given of 9 moles of water formed, so 9.0 moles of water. We multiply by a conversion, and note that we've put moles of water on the bottom, so we had moles of water, and now moles of water will cancel there. And we had 4 moles of ammonia for every 6 moles of water, and that means that now we get 6.0 moles of ammonia are going to be necessary to form those 9.0 moles of water. So remember that coefficients are exact, so we're going to treat them as if they have an infinite number of sig figs, and thus our answer should have 2 sig figs, because if we go back, we're given 2 sig figs here in 9.0 moles of water formed. This 4 is exact, that 6 is exact, and so we have 2 sig figs here, infinite sig figs here, infinite sig figs there, and so our answer has to have 2 sig figs. And that was mol-to-mol conversions.